with the degree of curvature that we identified from calculus and study guide and the definition of elastic curve function, now we want to find out relationship between the moment, shear, and elastic curve functions. So the next one we will have, let me cut one section here, and that section here we call that a dx differential slice dx, and what we have it in here when it become to deflect. So that portion with assume the moment, the curve, the positive moment, so it will be called the contraction on top and the expansion at the bottom outermost fiber, and the neutral surface somewhere between the top and the bottom here. And of course that the original dx differential slide dx, then it still be dx at the neutral surface, because as you can see the bottom expand, the top contract, so somewhere in the middle it will not change the length, and that actually neutral surface. And with that it have a curvature there. Then let's define the center of that curvature, and again I exaggerate the deflection, so that is the center there. So the associate angle here we call it d theta, and let's call the radius of curvature that we already defined, if determined from by definition, that is the radius of curvature distance from the center of curvature to neutral surface of the beam. With that definition, as you can see, from center to here, that is rho. And we also know in elastic bending, the distance from the neutral surface to the outermost fiber, that is C, right? That is C. So nothing new to us so far. And of course, if we have that C, then let's call the deformation at the outermost fiber, that is delta C. Here, if we make a parallel line, then we have the whole this is dx and this is delta C. So the whole thing for the outermost fiber at the bottom, it will be equal to dx plus deformation at the outermost fiber, dx plus delta C. So what do we have here? When it's small angles, what do we have? Tangent of the angle d theta on top there is about the same as d theta if we do it small angles. Otherwise you go back to review your calculus when we have the when we have an extreme small value theta about the same as sine theta, and tangent theta measured in radians, as you can see there from the study guys. And d theta, the angle is equal to the curve over the radius, so we can have it equal to dx over rho. And it also equal to, is also equal to, if we talk about the outermost fiber, so it equal to dx plus deformation at the outermost fiber delta C over rho plus C, over rho plus C. And if we cross multiply of the last equation, so let cross multiply. Cross what do we have? We will have rho dx plus c dx equal to rho dx plus rho delta c. So we can cancel this out. Cancel this. So what do we have here? And then we can divide. So we will have the equation is c over rho equal to delta c over dx. Over dx. And then you can see what is the ratio of the deformation over the original length. Do you recall that? So that normal strain, okay? And at the outermost fiber, that is the normal strain epsilon. At the outermost fiber, I call that epsilon c. And then if we assume linear elastic, assume linear elastic. So what do we have? We have epsilon. So normal strain equal to sigma normal stress at the outermost divided by the Young modulus E. E. And sigma c at the linear elastic, sigma c equal to mc over I divided by E. And simplify that, we have it mc over EI. So what do we have? So we have, let we replace, you see, c over rho equal to epsilon c, and epsilon c equal to mc over I. So what do we have here with that two equations? So we have 1 over rho equal to m over EI. And what does that mean? What does that mean? We can, because here, and 1 over rho equal to the second derivative of the elastic curve functions at here. So from that we can have the first important equation is cross multiply, and we have the moment at any point on the beam is equal to EI times the second derivative of the elastic curve function. So let's box that one here. Box that one. So from that, we can make a summary here. So integral beam equation. From that important equation from our transformation, we want to have some important equation here, and then we go on to practice the worksheet problem. Integral beam equation. What are the beam integral equation? So let me write the that equation back here again. Mx, moment at any point, equal to EI, second derivative of the elastic curve function. And of course, if you recall, in the shear and moment diagram lection, we have Vx equal to the change in moment, or the slope of the moment diagram equal to the shear. So it will be dmx over dx. So slope of the moment diagram equal to the magnitude of the share, as you recall that. And from that, as you can see, dm over dx, plug the previous equation, the top equation there. So we have what we have for Vx, we see the share related to the elastic curve function in the third derivative of the elastic curve function. And similarly, the it deflects if it goes down, and then we assume the Wx, of course, going down negative, then it that you can see there, it equal to dv over dx. What does that mean? The slope in the share equal to the magnitude of the distributed load. Magnitude of the distributed load. So, of course, the fourth derivative of the elastic curve function equal to the distributed load. 1, 2, 3, 4 x. Or we also have, if it opposite, if we take integral, then if you have from here and divide EI on the left, then you can have that the elastic curve function if you have the moment. So we can have what are the equation we also have from there. From the first equation here, mx equal to EI, I instead the y second derivative, let me take two integral, then we can have the elastic curve function, right? So we have let's go here, we have y x at definition, that is elastic curve function. So with that definition and the equation above, we can have it 1 over EI double integral, because that is the second derivative, and you can see there. So mx dx. So if you have moment, take the second derivative, divide by EI, we can get the elastic curve function. If we want to have the slope of the elastic curve function, then we take derivative, right? So it will be first derivative is slope function, and what is that? So it will be here equal to 1 over EI, and only one integral mx dx. Okay, so what is EI? EI is definition, as you can see, E stand for the material properties of that beam, I stand for the geometrical properties. So it here, the combination of this, it basically defined at the flexural rigidity, flexural. So it combines both the material and the geometry to determine how hard the beam will be deflected under the flexural stress or the internal bending moment. So it describes material and geometry stiffness of the beam. So basically that describes material and geometric stiffness of the beam. So that we done for the elastic curve function. We go ahead to practice worksheet 15a, and then we go back to do the superposition, and then we go back to practice again.